if you look at concrete, as I said, it is relatively complex. So, there are some empirical methods, semi empirical methods are there, right. So, essentially this is the amount of heat stored, right. So, that is again we assume that reinforced concrete temperature of rebar is 550 degree centigrade at failure, 550 degree centigrade at failure. Conductivity of concrete is very low, 1 to 2, and as I told you, more fire resistance dictates more cover, but cannot be increased infinitely or indefinitely. More the cover, more the strain in the steel, also extra material, so cost will increase. So, properties, if we look at it, how does properties vary? Thermal conductivity, for example, specific heat, for example, increases, and it is a function of type of aggregate. Yes, temperature, function of temperature, and with temperature it also depends upon aggregate. Wet concrete, of course, has got a very high specific heat, because wet concrete means water. Water has got very high specific heat, so it increases significantly there. Relatively dry concrete, calcareous concrete is somewhere here, calcium carbonate based, right. Gravel, some other gravels, some other carbonates, lightweight aggregates, granite concrete. So, specific heat varies in this manner. So, there are formulae available, for this I will just give you thermal conductivity lightweight aggregate concrete, it is nearly constant over a band, and for other concrete siliceous is somewhere there, right. So, generally for concrete it is in upper bound and lower bound, you will have something like this. So, you can see it varies from 2 to 1, and again it reduces with temperature. So, the some other results, normal weight concrete, lightweight concrete, that is the kind of band. So, lightweight concrete it does not change much thermal conductivity, but for normal weight concrete conductivity changes with temperature, it reduces down. Thermal expansion, it increases depending upon type of aggregate, shale, siliceous, carbonate aggregate, etc., etc. And you can see there are 4 components in the expansion of concrete. What are those? 3-4 components. So, with temperature is on this axis, if I look at the strain, if I try to do an experiment on a cylinder or cube, put them under compression and subject it to fire, what will happen? There will be some amount of thermal expansion. I put it under compression, remember. So, the compression is there, I am heating it, some amount of thermal expansion will be there, it will compensate the compression, So, this is thermal expansion total, and you might finally find an expansion occurring, you might finally find that there is an overall expansion. So, this thermal part, the compression part, then there could be some due to creep. So, measured net deformation might find much smaller compression than what you are what you are supposed to have, because the expansion will compensate for it and the creep also would compensate, relaxation might have some sort of creep would have also affected it. So, for concrete, whenever you are measuring such thing under load, all these aspects are to be taken into account, right. Anyway, so, for siliceous aggregate, again we have got thermal capacity given by this kind of a formula, it increases, right, up to 200 degree centigrade, 200 to 400 it is constant, 400 to 500 it reduces, and 500 to 600 there is a reduction, 600 it is again constant. Now, for siliceous aggregate, some experimental results, as I said, it is available in literature. Specific heat of thermal capacity is a function of temperature in this case as well. And remember, I said last class or sometime when I was talking about, I mentioned that concrete up to 200 degree centigrade, it's only free water will evaporate. So, all properties up to 200 degree centigrade is of one kind, 200 to 400 to 600 will be something different. So, that is what it is. 200 to 400 is again constant, 400 to 600, because some of those chemically combined water tends to go away, and once those water goes away 600 and above, your temperature it will be something like this. So, for carbonate aggregate the formulas are different, formula is somewhat different, but they are similar nature and similar results are available. I again do not expect you to remember, but you understand that it is a function of temperature and step functions. In fact, it is not, cannot be defined by a single functions. So, defined as fitted results are they can be results, fitted results shows there are segments, various segments, and you can so that is what it is. Thermal conductivity again is a function of temperature, it reduces with temperature, then it becomes at temperature equals to 0, this is 1.5, and this reduces temperature above 800, again it is constant, and greater than 800 slightly more. For quartz aggregate, these are the values. So, up to 800 degree centigrade, something like this. Quartz has got higher thermal conductivity amongst all the inorganic material. Quartz has got highest thermal conductivity. Pure quartz is of the order of around 10, steel is 50, but aggregate should be quartzite with lot of impurities and things like that, or similar sort of thing. So, from original quartz rock, if you have some aggregates, they will have thermal conductivity relatively higher. Carbonate aggregate concrete also shows some values of this kind, right, and that is how it is. So, the variation, thermal conductivities, heat capacity, all varies with temperature. This must be understood. Expansion is again properties is increases with temperature, and shale aggregate as I shown the earlier diagram. So, that is how it is. So, if I want to design for fire resistance, I got to take all this into account and do the heat conduction equation, solution of heat conduction equation. That is what we do not do. What we do is, in this class we are not doing this. The one way would be, some people have actually done some experimental work in 1980s, 70s and 80s, 1970s and 80s, and what they have seen is, if it is slab, if the fire increase in temperature, temperature as a function of distance from the exposed face. For example, for a slab, if this is the slab, this is the slab, and this is the slab, this is the slab, right, and exposed face is this one, exposed face is this is the exposed face, then this distance I am talking of, right. After 4 hours, if I go to 70 mm from the exposed face, the temperature will be 500, something like that. So, 60 mm from the exposed face, it will be something like this, 20 mm it will be very high, 40 mm beyond 800 is not really 40 mm. So, up to this, it means after 4 hours all concrete up to 40 mm thickness, 32 mm thickness or so would have actually disintegrated completely. There would have been spalling of concrete, right. So, 800 degree centigrade, I said that everything disintegrates, and half an hour, if you look at it at 20 centimeter, 20 millimeter, 2 centimeter, temperature is around 350. So, using this graph you can find out the temperature of the steel depending upon the cover depth. For example, if my cover depth is 30 mm, right, for the kind of concrete that they tested. So, cover depth is 30 mm, 550 degree centigrade is my 550 degree centigrade is my time, condition criteria. So, I draw a line at 550, 30 mm, the fire resistance will be slightly less than 1.5 hours. It will, this half hour line is this, 1 hour line is this, 1.5 hours line is like this. So, it will be slightly less than 1.5 hour. If I have 20 mm cover, then 550 actually 20 mm cover, it would be more than half an hour, but this would be slightly more than 1 hour. So, this is how we can find out, this is a simple way to actually, but then this is specific to specific type of aggregate where experiments were done. This is available in a book by Malhotra in UK, so they did quite a bit of experiments. Anchor and Malhotra, their books gives you. So, this is for dense concrete slab. For lightweight aggregate concrete, similar curves are available. So, for slabs you can actually find out very simply using this sort of curves. For column or beam members, temperature contours are given, right. Temperature contours are given. So, this for example 100 degrees centigrade, 200 degrees centigrade at a given time. So, similar graphs are available for various times, right. So, supposing you know the cover depth, right. This is given at, as I said, at different times. The time at which that the cover depth this temperature reaches 550, you can find out the corner steel and so on. So, such curves are given for various time, each curve for one time, and the contours, temperature contours are available, and it is assumed that it is symmetric and fire, it is engulfed in fire from all sides. So, this is a kind of diagram. Isotherms are given and distance from the surface and temperature, 60-minute exposure. As I said, for each time there is one set of graph. So, 60-minute exposure, right, this is 50 degrees centigrade, okay, and 150 degrees centigrade, etc., distance from the surface. So, distance from the surface 30, say let us say 30 mm, distance from the surface wherever it is. Corner steel you will consider the diagonal distance. So, 30 mm, you can see that 400 degrees centigrade for this is one, this is half width of the beam depending upon the beam size. So, if the half width of the beam is 150, in other words this is 300 mm and this is also 300 mm. So, that is how you can actually, such curves are available for concrete and one can obtain them. So, this is one way, but looking at graphs and things like that is fairly complicated these days, and this was for a specific case. There is a slightly better formula, empirical equation, and that is easy to calculate because you can put it in Excel sheet, spreadsheet or somewhere, and much easy to calculate today. This we know. Now, the formula is given as that the temperature rise of the concrete is given delta T c is a function of some n w, n x and delta T g. Now, let me define each one of them. N w is a function of time, n w is a function of time, n x is the function of distance from the surface. So, n x is given like this, delta T represent temperature rise, subscript C and G denotes concrete and gas. So, delta T g, so this is the concrete temperature rise, delta T is the gas temperature increase, that I can find out as 345 log 8 T plus 1, that is equals to delta T g, right. This is I can find out, and this delta T c concrete temperature rise I want to find out. N w is a function of time. As the time increases, this value would be smaller, because 1 minus 0.06 divided by T to the power 0.88. So, this tend to be, so when this T is actually infinity, this term should tend to become 0. So, this term will tend to become 0. So, N w will tend to become 1. That means, nearly same as it is 1, the factor is maximum 1, minimum is some smaller value fraction, and this is related to properties of the concrete and the distance from the exposed surface. Let us see how it is, because this is given as u x. So, n x is equals to 0.18 ln u x minus 0.81 empirical. As I said, u x is a function of x, the distance from the surface, and thermal diffusivity of the concrete. So, T is the time in hours. Now, since it is empirical, the unit is very important. T is the time in hours, x and y are distances in respective direction from exposed surface. U x, that was I just talked about, because I said that n x is equals to it was how much, Nx was equals to 0.8, right. So, 0.18 ln Ux minus 0.81. So, Ux is given by A by AC T by x square, right. Now, what is A and AC? A is A and ACs are thermal diffusivity, because it depends upon thermal diffusivity. If the thermal diffusivity is high, it would cover more distance. What is the unit of diffusivity? Unit of diffusivity is, unit of conductivity is watt meter degree centigrade, right, and density is kg per meter cube. C is joules per kg degree centigrade. So, rho C is simply kg will cancel out, joules per meter cube degree centigrade, and if I have k over rho C, which is thermal diffusivity, k over rho C. So, what is nothing, joule per second. So, you will have k over rho C. So, thermal diffusivity A is joules per second degree centigrade divided by joules per meter cube degree centigrade. So, degree centigrade cancels out, right, and there is a meter also, joules here. Thermal conductivity is watt meter degree centigrade. So, there was a meter, there is a meter here. So, this meter. So, actually you can see A is simply meter square per second. Let me just write it clearly for you to recollect. What is joules per second? So, conductivity unit is this, conductivity K unit is this, joules per second, which is what, meter degree centigrade, right, and specific it, rho is kg per meter cube multiplied by joules per kg per degree centigrade. So, you will have this cancelled out, and this cancels out, this and this cancels out. So, you will be left with meter cube divided by meters second. So, it is meter square per second. Now, you can see that T is what, second, x is meter square, same unit. So, this actually this term is dimensionless. So, Ux will have a term, Ux, this term will be dimensionless, because A is thermal diffusivity, this is also thermal diffusivity. One of them is taken as constant, one of them is taken as constant, we shall see that. So, one of them is taken as constant. So, Ux is related to, it is in this manner. Okay. Now, A is the thermal diffusivity of the concrete that you are your concrete, and subscript C is for some reference concrete, which is constant. So, reference concrete value is taken as 0.417 10 to the power minus 6 meter square per second, right. Now, let us see typically what will be the value of thermal conductivity, thermal diffusivity of concrete. You see, if it is 1.5 watt meter degree centigrade, right, K, rho of concrete is 2000 by rho C. So, rho is 2400, C is around 900 or 1000, let us say, right, 900 or 1000 joules per kg per degree centigrade. So, 1.5, so 1, 2, 3, 4, so it will be something like 1.5 divided by 2.4 into 9, right, or it would be how much, 2.4 into 9, let us say, is 222 point something. So, it would be 1.5 divided by 2 point something into 1, 2, 3, 4, 5, 10 to the power minus 6 or minus 6, something of this order, right, something of this order. So, if it is less conductivity, this value will be still lower. So, reference concrete is taken to be. So, you can see this order of 10 to the power minus 6, because 1.5 or 1 divided by, let us say, 2.4 into 9, 1, 2, 3, 1, 2, 0.9 you take. So, 2.4, so 10 to the power minus 6. So, this is the order, and this is the reference concrete. So, reference concrete is taken to be this, Ux will be found out in this manner. Then you can find out delta Tc. Delta Tc was equals to N x N W delta T G. N W is 1 minus 0.06 t to the power minus 0.88 or something, right, and this was 0.18 ln ux minus 0.81, and ux is simply A, your thermal diffusivity of your concrete divided by 0.417 into time at which you want to calculate out and into the distance square. So, you can find out at any distance from the surface at a given time what is the temperature rise. So, if your cover depth is 25 mm, take x is equals to center of the steel bar. So, not the clear cover plus diameter of the bar, nearest steel, and x you will find out, x has to be in meter, t has to be in hour, and that is how you can find out. You can calculate this out, you can find out and find out the temperature. When it becomes 550 T, you can find out corresponding to 550, and that would give you the fire resistance. For biaxial, the formula is somewhat modified, like this was for slab, for a column or a beam, biaxial scenario. So, now NW remains same, NW remains same, delta Tg remains same, Nx and Ny formula gets modified. Now, what is Nx? Same, A by AC into T by x square. What is Ny? Ny is simply same, A by AC T by y square. So, if it is something like a ux and only, so correspondingly to ux will formula will be same. So, ux you find out in this manner. So, this is x, this must be the y, this must be the y, right. So, you find out in the same manner ux and uy. So, formula becomes now something like this, but there is one problem, limit for this formula is valid for certain cases, because it assumes the heat temperature on the other surfaces are not increasing, it remains constant. That means, fire temperature never reaches there. Assume one dimensional heat transfer or two dimensional heat transfer, and the other boundary is constant at ambient temperature. So, that is why this condition is there, x should be less than 2L minus 3.60015 T that you are finding out. What is L? L is the thickness of the section in meter, and surface temperature rises Nw into T. That surface temperature we are assuming is Nw into Tg, because this will this will, depending upon the time, we are at infinite time, temperature this will become 1, this will become 1. So, using this formulae, you can then therefore find out the fire resistance of RCC section also, thermal design for fire resistance. Structural design would involve computing the structural capacity, stability and all that, but thermal design, structural design, whichever is more critical, that would govern the overall fire resistance, right. Okay. So, just as an example, like we did for a steel, let us do it for a slab, simple case of thickness 125 mm, thickness of the slab, covered depth is 25 mm and bar diameter is 10 mm, clear covered depth is 25 mm. Find the temperature of the rebar after 2 hours for reference concrete. So, just made it simple. Now, A by AC will be 1 because it is for reference concrete. So, ux will be simply T is 2 hours divided by x is 25 plus 5 plus 10 by 2, right. Sorry, x is equals to 25 mm is the clear cover at the center of the bar, 10 by 2. So, which becomes actually 30. So, x is equals to, so x T is 2 hours by 30.3 square, because it has to be in meters. 30 mm is 0.03, 30 mm because 10 mm plus 25 mm, 30 mm is 0.03 square. So, that is actually our ux, and use this formula to find out after 2 hours what will be the temperature, because Nw is equals to simply 1 minus 0.06 into T to the power 0.88. So, this is 2 hours, ux you can find out, hence Nx you can find out, and then you can find out the delta T c, because delta T g after 2 hours is known, you can find out delta T c. So, that is how one can obtain, right. So, fire resistance of concrete also we can estimate for temperature or thermal, for thermal scenario approximately by this formula. Okay. Right. Now, some more data related to mechanical properties of. So, this is one formulae, the cube strength as a function of epsilon c is the relationship between stress strain relationship. The compressive strength is related to epsilon c stress strain curve, right. This is the maximum value, epsilon max is the maximum in normal temperature condition, and if E c is greater than E max, this is the formula. So, stress strain relationship for concrete as a function of temperature is also available. If it is greater than 450 degree centigrade, this is the formula, where this is the original ambient temperature maximum strength. So, such formulas are available. Greater than 450, this is the value. So, epsilon max is given by this formula as a function of temperature. So, one can obtain stress strain relationship of concrete depending upon the temperature, if one is interested in calculating in detail mechanical performance, right. But simple case, this is simple, this much easy to even remember. This can be used in residual post fire residual evaluation as well. So, 20 to 300 degree centigrade for dense concrete, it is taken as approximately strength reduction factor is taken. So, this reduction factor is less than 1. If the concrete strength, mean strength, let us say is 30 multiplied by this factor, say 200, if T is equals to 200 or 300, let us say T is equals to 300, how much will this value be? 300 by 6000, 300 by 6000. So, it is 0.5, 0.05. So, this would be 0.95. So, at 300 degree centigrade, the strength would be 0.95 into 30 MPa. So, strength reduction factor fraction at 300 to 800, then you can find out how much the value would be using, say for example, 600, this will become 300 divided by 588.95 minus this. Similarly, for lightweight concrete, up to this we do not consider any strength reduction, beyond this reduces the loss slope. Steel similar, and beyond 300, this is the formula, pre-stressing steel, this is the formula. So, one can actually obtain how much is the strength after it has been exposed to a fire temperature, right. This is from UK results. Well, such results are not available in many places in the world, because the empirical results, but one can roughly use them for our purposes. Design for fire resistance is, of course, if you look at it, masonry, if we look at quickly, masonry temperature versus specific heat increases, and same brick thermal conductivity is of this kind. Not much studies are available on brick. So, that is what it is. So, having looked at the fire resistance concepts and design of structural members, some members not structural, it could be for non-structural members also, for fire resistance design for fire resistance from thermal point of view. Now, we can look into some of the planning aspects. Fire protection is not structural fire protection alone, that is actually much later, because first I should have a good planning, so that, as I said, fires should not initiate, and if it initiate, it should not spread. So, then we should look into some of the concepts of functional planning, a little bit concepts, because it is related to occupancy type and all that, and since my course is also related to a little bit of functional planning otherwise. So, we will define certain things. For example, urban neighbourhood and microclimatic modification I will just mention, because as we have seen, as you see maybe some other course related to functional planning of building. Functional planning of building starts from urban planning stage itself, and smallest unit of urban, smallest unit of urban neighborhood, urban area for planning concepts is called a neighborhood. And this was given by this gentleman Clarence Perry in 1925 in United States of America. Residential unit, this is for residential unit, the unit neighborhood is the smallest residential unit in urban planning, right. Now, whole thing here, it would look, it should be bounded by main arteries. So, this is a kind of a neighborhood. This is bounded by main arteries. They call it, in US they would call it highways, because there are highways in the city. No major artery should pass through them, no major road, and you can interestingly see many of these concepts have been actually used in Delhi, New Delhi area, later on in after post independence. For example, R.K. Puram. So, you go to R.K. Puram sector 1, sector 3, which is very close to IIT actually. R.K. Puram sector 3, 4, you will find no major artery pass through them. It is actually private road for those people. And the primary location, primary aspect, that what is the focal point of a neighborhood is usually the primary school. The concept that was developed by this gentleman is excellent concept actually, although it is a bit consumes a lot of space, is that no children, primary school children should walk to the school, maybe play around, kick a ball or do something and reach to the school, right. Well, that is not the case in Indian society. They are so pressurized, the children are so pressurized even at nursery level, because they have to go through a competition. Sometime they, in fact, you have a pre-primary school or maybe a play school where they teach you such things which will make you to get into the regular school and things like that. Of course, now they have made it a little bit over the last couple of years. The judicial system and all coming in, they said that the school should be within certain distance, right. Otherwise, it was all messy. But in any case, according to his concepts, the primary school is a focal point. So, it should be somewhere here. So, primary school is the focal point of such a neighborhood, all right. And community center, maybe a church that is shown here, similar sort of thing, or temple or a mosque or whatever it is, depending upon the community, that would be at the center. And the market, local market, not a big market. This was the concept, but this concept keeps on changing. Maybe with the modern malls things could have been different, maybe 3, 4 or many neighborhood would have such a mall, but irrespective of that, this is the concept. And this arterial road and the interior roads are light surfaced, right. So, there will be some local recreation area and light surface only for private vehicles, no really thoroughfare should be there to such one of them, right. So, basically what it assumes is home is the home. So, comfortable distance from the home to primary school is considered to be 1/4 of a mile, because this was in US, and high school is thought to be about 1 mile. Now, 1/4 of a mile means a child should be able to walk 1/4 of a mile, something in our kilometer terms would be about 0.4, no less than 500 meter, somewhere around 1.6 kilometers a mile. So, divided by, you get around 400 meters. Now, a small child 3 years old, 4 years, they might go to kindergarten even still slightly higher age, but in 1925 maybe people might have been going up to 5, 6, and so whatever it is, 3, 4 years child, they should be going on their own and should be able to walk. No vehicle should be taking them. High school is 1 mile, and then working place should be about 3/4 of an hour travel, and hospital etc. should be here. Recreation could be 1.5 hours of travel and things like that. So, this was the concept, that your main workplace, let us say Central Secretariat, Connaught Place, or for that matter something of that kind, should not be more than 3/4 of an hour. Major hospitals, local hospitals should be, so hospital, working place, that should be 3/4 of an hour. So, local hospital could be there, or local medicine center or something at the community center could be there. So, that is the concept of urban neighborhood. So, therefore, based on this kind of concepts, occupancies are developed. So, this is just I briefed it, because urban urban planning could be itself a subject by itself. So, there are varieties of occupancy which are there in 9 types of occupancy which we have divided all the types of building. National Building Code gives you A, B, C, D, E, F, G, H, I, J occupancies. So, we will start from here in the next class, because planning, everything has to be looked into. It starts from urban planning. We have these different types of occupancies, and we segregate that in such a manner that the one which is sensitive to fire is away from fire generating one, fire hazard one. Okay. So, I think we will close here, we will stop here, next class we will look into it.